Traditionally, one of the trickiest and most time-consuming aspects of CFD has been the geometry meshing stage. The fluid and solid regions are discretized into grid cells, which is then passed to the solver for solution. It's normally at this stage that requires the geometry to be simplified for meshing or simulation compromises made for the sake of solution time. FloEFD uses proprietary smart cell technology to alleviate a lot of the issues associated with the old way of doing things. Smart cells can have multiple fluid and solid volumes to simplify the mesh generation step. Complex CAD models are meshed with minimal user input using an automatic mesher. Solution adaptive mesh refinement can even increase grid density mid-solve based on local flow gradients. If we go normal to the screen in NX, we can show the global mesh settings for FloEFD. At present, the automatic mesh is applied at level 4. We can move the slider to increase or decrease the global mesh density. FloEFD uses a finite volume method on a Cartesian grid to solve the Navier-Stokes equations. The mesh on the screen is only the base mesh before any cell subdivision has occurred and is visualized to give the user a rough idea of how fine the final generated mesh will be. The mesher can be switched over to manual settings if desired, where cell sizes and refinement settings can be accessed. User-defined local initial meshes can be employed to manually apply finer grid on specific parts and areas in the model. The mesh has already been generated for this model, so now let's have a look. If we zoom in around the base plate pins, we can see a finer mesh around the heatsink where the flow is constricted. The current plot is colored by levels, which can range from 0 to 9. Octree refinement is employed to split a single base mesh cell into 8 smaller cells to increase to the next mesh level. This can happen up to a maximum of 9 times to create exponentially smaller cells. This Octree method performs 2 important tasks. First, the aspect ratio of every cell is identical. The smallest cell has the same aspect ratio as the base mesh. The second is that the growth ratio is restricted to a single level to avoid very small cells transitioning into large cells. These are both important for solver robustness and convergence behavior. The smart cells are always found at the interface between fluid and solid. This is where the boundary layer forms and the convective heat transfer occurs. Smart cells can have multiple control volumes, up to 12 in a single cell. It's this technology which makes FloEFD meshes easy to generate and tolerant of dirty CAD geometry. If we plot the surface of the heatsink base with mesh, we can see the smart cells which touch the water region. Proprietary wall functions are used in the smart cells to apply the boundary layer. FloEFD uses the K-epsilon model for the bulk flow turbulence and an empirical engineering model for the near wall effects, which have been calibrated over a wide range of Reynolds numbers. Now let's have a look at the solid conductivity in a 2D plot through the model. A smart cell can have multiple solids within a single cell, up to 36. This makes resolving thin solids, such as thermal interface materials, very straightforward and easy. When overlapping parts exist, such as between the sealing O-ring and the base plate, there is a material hierarchy which can be edited to get the correct material dominance. The benefits of FloEFD's unique mesher are that it's very simple for a non-expert to generate an accurate grid. The boundary layer is handled automatically without the high cell count requirement at the wall. The mesher has a default automatic setting which can be augmented with manual conditions if desired. To summarize, we saw how FloEFD discretizes the domain into finite volume grid cells using an immersed boundary approach. The FloEFD smart cells remove a lot of the complexity of meshing, which has traditionally been a stumbling block for reliable CFD results. FloEFD removes these barriers and allows non-experts to generate a robust mesh.